All right, so this problem, this half pipe problem, is about a skateboarder who's going down this half pipe. The skateboarder in the drawing skates with some velocity. We're given the velocity at the beginning here, down the left side of a half pipe that is a perfect semicircle whose radius is 4 meters. So we're given the velocity at this point, and that's 6 meters per second. And we're given that this radius is 4 meters. The first question is asking, ignoring non-conservative forces, calculate the height h of the highest point reached by the skateboarder. There are two ways of tackling this first part that are equivalent, but I'm gonna do them both ways to illustrate how you can use both things. So since I'm thinking about the work energy theorem, which says that the work is equivalent to or associated with a change in energy, and one form that I really like because I can manipulate however I like is this form that says that the change in kinetic energy between two positions, kinetic energy at point 2 minus kinetic energy at point 1, plus the change in potential energy, which is also between the 2 points 2 and 1, is equal to the work that is being done by non-conservative forces going from point 1 to point 2. And like I said, this is just one formulation of many formulations that you could have. And I like this one because I can manipulate it to get all the other ones. This, of course, comes from the first statement of the work energy theorem, which says that the total work done is associated with a change in the kinetic energy. But the total work done has an unconservative part and a conservative part. And the conservative part, so far, the only force that we know of that contributes to the conservative part is the gravitational potential. But there are other forces that could contribute to this part. But for now, it's just equal to the change in the potential energy minus the change in the potential energy is the work done by a conservative force. So I can sub that in. And I find the form that I like, which is the work done by non-conservative forces is associated with the change in kinetic energy and the change in potential energy. If I write the changes as the differences between the final and the initial kinetic energies and potential energies, and I just algebraically manipulate this by combining the things at the position 2 together and the things at the energies at the position 1 together, I find that this is equal to the difference in energy, the total mechanical energy at position 2 minus total mechanical energy at position 1. And in the special case in which non-conservative forces do no work, then of course this reduces to delta KE plus delta PE is equal to 0. And that means that if I do the same manipulation, then the difference between E2 and E1 is going to be equal to 0. That means that mechanical energy is conserved. So the two key things the two ways that you could tackle this problem is you can start from this equation, which I typically like, or if you know that you are in this regime where the non-conservative forces are doing no work, then you can start right away with the conservation of mechanical energy. So let's see how we could do it with either one of these. Let's start with this one, this formulation. So I'm gonna say that first of all, I'm talking about differences in kinetic energies and potential energies and the work done by non-conservative forces between two positions, position 1 and position 2. So for the first part A, it's asking about the highest point reached by the skateboarder. So this is some position, which I could call position 2 or position 1, it's up to me. But let's call it position 2, for example. It's the position at which the skateboarder reaches the highest point. So I'm going to call that position 2. And I'm going to call the position that I know something about as position 1. So right here is position 1. And then I could apply this equation between the two positions. And this is always true. The special case, of course, is if the non-conservative forces are doing no work, which is the case in part A. When it says ignore non-conservative forces, that means that they do no work, zero work. So that means that this is going to result to delta KE plus delta PE between the 2 points 2 and 1 is equal to 0. They sum up to 0. So I start with writing up this particular statement of the work energy theorem. This is the change in kinetic energy from 1 to 2 plus the change in potential energy from 1 to 2 is equal to the work done by non-conservative forces from 1 to 2. And in this case, because I'm ignoring non-conservative forces, this is going to be equal to 0. And the change in kinetic energy, of course, is equal to the kinetic energy at point 2 minus kinetic energy at point 1. And the kinetic energy is given by, the kinetic energy, of course, is a kinetic energy associated with motion. Remember, for the word kinetic means movement or motion. So that right away, I'm thinking about the energy that's associated with some velocity v. And in particular, kinetic energy is equal to half mv squared. And it's a scalar quantity, so I only need the magnitude. And its units are joules. Its SI units are joules. And the change in kinetic energy is the kinetic energy of the final situation or position minus the kinetic energy of the initial one. So if I'm talking about changing kinetic energy between 1 and 2, the position that I know something about and the position that I want to calculate something about, then I can write it as the difference between the velocity, the kinetic energy at position 2 minus the kinetic energy at position 1, where m here is the mass of the skateboarder and her skateboard. So the whole system that is moving. And then the change in potential energy is going to be equal to the difference between the potential energy at the beginning, at the final position, minus potential energy at the initial position. And the potential energy is, of course, the energy associated with being at some height h in a gravitational field. And in this case, it's going to be equal, because we're at the surface of the Earth, it's going to be equal to mg, gravitational potential of Earth, multiplied by the height from some datum that I measure from. And the difference in potential energy would be 2 minus 1. So this h in this equation could be measured from wherever I decide to be my reference, my h equals 0. I could make my h equals 0 up here. I can make it right at this edge here at the position 1. I could make it right at the bottom, or I could make it anywhere I want. In fact, I could put h equals 0 wherever I want. Let's just, for simplicity, put it at one of the positions, and we could pick position 1, for example, to have h equals 0. And that means that then the difference between the height 2 and height 1 is going to be equal to h, the thing that we're looking for, the height h of the highest point reached by the skateboarder. So then the potential energy difference, delta PE 1 to 2, is equal to PE 2 minus PE 1, which means that it's equal to mg h2 minus mg h1. And of course, we said because non-conservative forces are being ignored, then this is equal to 0. And there's a nice thing here, the reason where if it's equal to 0, I can right away divide both sides by m, and therefore m would drop out of the equation because 0 divided by m is still 0, and m by m is equal to 1, so this m would just drop out of the equation. And then now I'm left with half v2 squared minus v1 squared plus g h2 minus h1 is equal to 0. Okay, so what do I know about these positions? I know v1, so I know that v1 is equal to 6 meters per second, so this I know. I know that at the second position, at the highest point reached by the skateboarder is, has some velocity going up and then reaches 0 and then flips direction and goes back down. So right at the highest point, the velocity of the skateboarder is equal to 0. So then I know that this will be equal to half 0 minus 6 meters per second squared, 6 meters per second all squared, plus g, which is 9.8 meter per second squared, multiplied by the difference between the two heights, the height 2 minus height 1, and that's straight up h. So in fact, I didn't even have to specify where my 0 point was, because all I need is just the difference between the two heights. In other words, I could say that, if this is my h equals 0, then h1 would be equal to 0 and h2 would be equal to h, which is what I'm looking for. Or if I had put, for example, this to be my h equals 0 instead of this, then my h1 would be this distance, which is essentially the radius of the half pipe. So that's 4 meters, and my h2 would be the 4 meters plus h, and 4 plus h in this case is h2, and h1 is just 4. So h2 minus h1 is h. So whether I choose my h equals 0 here or here, I get that the difference between h2 and h1 is equal to h. So in fact, it doesn't matter where I choose h equals 0. So then this is h2 minus h1 is equal to h, and that is still equal to 0. And from this, I find that h is equal to, v1 squared over 2g, which is 6 meters per second squared over 2 times 9.8 meter per second squared. And that's meter squared over second squared divided by meter over second squared. So second squared goes with second squared, and meter squared over meter gives me a meter, and h is in meters, so that's perfect. 2 times 9.8, that's roughly 20. That's 19.6. And this 6 squared is 36. So it's 36 meters squared per second squared over 19.6 meter per second squared. And that, if you work it out, gives me 1.84 meters. So that's one way to solve this problem, using this formulation of the work energy theorem. Another way to tackle this, which is an equivalent way, in fact, is to look at the formulations, the different ones, and to say, in the special case where I know that the non-conservative forces are doing 0 work, then energy 2 is equal to energy 1. That is to say, the mechanical energy is conserved. And in fact, the mechanical energy is conserved, meaning it's conserved throughout the path of the skateboarder. When she's here, when she's here, when she's here, when she's here, she has the same total mechanical energy, independent of where she is. How does that work? Well, you see, when she's going down, that means that her potential energy is going down, because the potential energy is equal to mgh. So it's mg multiplied by some height. if I, for example, choose this to be my h equals 0 at the bottom here, that means that when she was up here, she had some potential energy. And of course, she had some kinetic energy because she had some velocity. But as she's going down, her potential energy is going down. But because the mechanical energy is conserved, in this case, that means that the kinetic energy is getting higher as she's going down, right? Because the energy, the mechanical energy, is equal to the sum of the kinetic and potential energies. So if her potential energy is going down as she's going down the half pipe, then that means her kinetic energy is going up. Okay? And in fact, her mechanical energy is the same throughout the path, including point 2. So what I could have said is, this is an equivalent way of doing the problem. I could have said the work done by non-conservative forces is equal to 0. That means that mechanical energy is conserved. Which means that the sum, so the mechanical energy, which is equal to the sum of the kinetic energy and the potential energy, is conserved. That means it's a constant. That is to say that the kinetic energy at some position 2 plus the potential energy at some position 2 is equal to the kinetic energy that I started with plus the potential energy that I started with. Okay, that is the statement of the mechanical energy is conserved. So if I figure out what the kinetic energy at position 2 is, that is because the velocity is 0, then I know that the kinetic energy is going to be equal to 0 because the kinetic energy is equal to half mv squared. The potential energy at position 2 is equal to mgh, and like I said, I can measure it from any point I like. Let's say I'm going to measure it from the bottom point here, so that means that the height of point 2 is equal to 4 plus h. So the potential energy is going to be at this position is going to be mg 4 meters plus h. I apologize for using m and m for meters and for mass, so I'm just going to use capital M for mass to differentiate. And then for position 1, the kinetic energy 1 is equal to half m times v1 squared, which is 6 meters per second, all squared. And the potential energy at position 1 is mg times, I'm measuring, remember, in this case, I decided to measure from here, h equals 0, but I could have measured straight from here and made it easier for myself, but doesn't matter. Here, at position 1, the height is 4 meters. And again, this is the mass m. I'm just using capital here to differentiate between the meters and the mass. So in fact, I could have done the same thing up here, just to make that distinction. So in this case, again, I could divide both sides by m, and then m by m is going to be equal to 1, equal to 1, equal to 1. So m actually falls out, and I don't have to worry about it. And then if I just look at h, which is what I want, I find that gh is equal to, I'm going to remember to take this to the other side. So that's half 6 meters per second squared plus g times 4 meters And what's left from this side is g times 4 meters. And these cancel with each other, which is another confirmation of it doesn't matter where you choose your h, because the difference is going to cancel out. And then what you get in the end is h is equal to 6 meters per second squared. Sorry, it's all squared. 6 meters per second all squared divided by 2 and g, which is 9.8 meters per second squared, which is exactly the same thing that we got from the other approach. Now for part B, it says, ignoring non-conservative forces, so I'm still in the same regime as before, calculate the maximum speed achieved by the skateboarder. So the first thing I gotta decide is, where does she achieve this maximum speed? At which point in her path? So remember when we said that the mechanical energy was conserved throughout her path, we said that here, let's say I'm going to choose this to be my h equals 0 just for simplicity. And I'm looking at my kinetic energy, my potential energy equations, and my equation of conservation of mechanical energy in this special case. In this special case, the energy at some position 2 is equal to the energy at some position 1, independent of where these positions are throughout the path. So I know something about this position 1. I also know something about this position, so I could use either position as my reference. But let's say that I'm going to use just this position 1, just in case I made some error in calculating what h is. I'm just going to keep using this as my position 1. And I'm going to say that the energy at this position 1, the total mechanical energy, which is the sum of the kinetic energy and the potential energy at position 1, is the same as the potential energy at any other point throughout the path. And to figure out where the maximum speed happens, I got to consider what's going on with the kinetic energy and what's going on with the potential energy. The potential energy of the skateboarder, if she starts out from here, as she's going down, h is decreasing, so her potential energy is going down, 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 and then it reaches its minimum value right when she is at the minimum height, and then the potential energy increases back again until it reaches its maximum value when the skateboarder is up here. The kinetic energy, on the other hand, starts out here at some value, and then something happens to it, and then it reaches 0, which is its lowest value, right at the highest point here. So since I know that the mechanical energy is conserved, that means that if the potential energy is going down as the skateboarder is going down, that means that the kinetic energy is going up. So that is to say that the point at which kinetic energy is maximum is the point at which the potential energy is minimum. And the potential energy is minimum right at this point. So right at this point, which I'm going to label as point 3, which is the lowest point here, I have minimum potential energy, which means I have maximum kinetic energy. Okay, so to calculate the maximum speed, I got to calculate the kinetic energy right at this point 3. And to do that, I could do it either way like I've done before, either using the conservation of mechanical energy statement or this statement of the work energy theorem. The change in kinetic energy between positions 1 and 3. 1 is here, 3 is here. plus the change in potential energy between 1 and 3 is equal to the work done by non-conservative forces between 1 and 3, but the work done, because I'm ignoring non-conservative forces, this is equal to 0. The change in kinetic energy, like we've noticed before, is half m. Then because I'm going from 1 to 3, it'll be v3 squared minus v1 squared. And the change in potential energy will be half, sorry, no halves, just to remind myself. Potential energy is just mgh, so mg, and then I'm going from 1 to 3, so it's h3 minus h1, and that's equal to 0. I could divide both sides by m, so this goes away, and I'm left with the differences between the velocity squared and the h's squared. So I gotta figure that out. If I just redraw this very quickly instead of just keeping to move the paper, this is position 1 and this is position 3, and I could choose my h equals 0 anywhere. All that matters is the difference between the two, and this is h1 minus h3 is equal to 4 meters, which is the radius of this arc. So this is 4, this is 4. At the lowest point, it will be 4 meters. So the difference between h3 and h1 is 4 meters. However, 3 is lower than 1. So this is minus 4 meters. So then I know that if I take it to the other side, it's going to be plus 4 meters. And then I multiply by 2. So I know that v3 squared is equal to v1 squared plus 2 times 4 meters times 9.8 meter per second squared. Okay, and I know that this is the velocity at point 1 is equal to 6, so that's 6 meter per second all squared plus 2 times 4 meters times 9.8 meter per second squared. And let's check the units. That's meter squared over second squared. That's meter times meter. That's meter squared over second squared. So I can add these, and that'll be okay. And then when I take the square root, it'll be meters per second again. So this is equal to 36, and this is 8 times 9.8. So that means that V3, if I work it out, 30, will turn out to be 10.7 meter per second. Another way I could have done this is I could have used the statement of conservation of mechanical energy, just like I've done in part A. So for example, I could have said that because the work done by non-conservative forces is 0, then that means that the total mechanical energy at some position is the same as any other position. So I could have picked, for example, to compare positions 2 and 3, because at position 2 the velocity is 0. That means there is no kinetic energy, so all the mechanical energy is in the potential energy. And at position 3, if I choose my h equal to 0 be exactly at position 3, that means that the potential energy is 0, so all of the energy is in the kinetic energy. So that means that the kinetic energy 3 is equal to the potential energy 2. So from the statement of conservation of mechanical energy, I get that choosing h equal to 0 right at position 3 will give me that the kinetic energy at position 3 is equal to the potential energy at position 2, where position 2 is at the highest h achieved by the skateboarder. So the kinetic energy at position 3 is half mv3 squared, and the potential energy at position 2 is equal to mg, and then h in this case will be the h that I found for the difference here between the two positions, 1 and 2, plus this height, because I'm referencing from this point, h equals 0, so that's 4 plus the 1.84 meters. So that's 4 meters plus 1.84 meters. And again, the m goes away, and I get v3 squared is equal to 2 times g times 5.84 meters, and that will give me the same answer. Now for part C, we're asked, in a more realistic situation, non-conservative forces do exert some negative work on the skater. Do you expect her to attain a higher or lower maximum height compared to what we've calculated before, and why? So the first thing I'm thinking of is now be in a situation where the non-conservative forces are exerting non-zero work. Then if I look at my statement of the work energy theorem, I find that the change in kinetic energy plus the change in potential energy is equal to the work done by non-conservative forces. And it used to be for part A, which is what we're comparing to, that the work done by non-conservative forces was 0. Now it has some negative value, and I want to know what will happen to the height, the maximum height attained by the skateboarder. So if you remember, we said that this was equal to difference in kinetic energy was half m, and if I'm comparing the two positions, 1 and 2, where she attains the maximum height, and the difference between them is height h, and this is where v equals some number that is 6 meters per second, and this was v equals to 0 at point 2, then the difference in kinetic energy is going from 1 to 2 is equal to half m v2 squared minus v1 squared, and the change in potential energy is equal to mg, and I'm going from 1 to 2, so that would be h2 minus h1, and that will be equal to the work non-conservative going from 1 to 2. I know that v2 is equal to 0, so this is going to drop out. So this is going to be minus half m v1 squared, so I'm going to take that to the other side, and I'm going to say that mg h2 minus h1 is equal to half m v1 squared, because this is 0, plus the work done by non-conservative forces. This is the h that I'm looking for. mgh is equal to half m v1 squared plus the work done by non-conservative forces. So you could see that if this work goes from 0 to some negative value, that means that the right-hand side now is going to be a smaller value, and that means that the h would be a smaller value. So h is going to be lower in this case. And this is the proof right here. Why? Is because of this. Because now, when I'm doing a negative work with non-conservative forces, I'm going to take away from the kinetic energy that I started with, and I'm going to have less energy left to attain some difference in height to transfer to potential energy, which means that the height is going to be lower. So less available energy to convert to potential energy. So let's put in some numbers in part D, where it says if the friction force, which is a non-conservative force, we know, for example, that the forces that we know of that are non-conservative, we know that friction force, tension, air resistance, the normal force, all these forces are non-conservative forces. And so the friction force is a non-conservative force, so any work that it does is going to be a contribution to the work done by non-conservative forces. And the question is saying if it does minus 0.5 joules of work on the skateboarder for every meter she is in contact with the half pipe for every kilogram of her mass, calculate the new maximum height. So the total work done by friction, which is the total work done by non-conservative forces, is going to be equal to minus half joules multiplied by, if for every meter she loses half a joule, that means it would be half joules multiplied by the length of contact. So whatever length of contact she's is in with the half pipe, for every meter of that, she's going to lose half a joule. And for every kilogram of her mass, so multiplied by her mass. The length of the contact in meter, I was told in the head of the problem that the half pipe is a perfect semisphere whose radius is 4 meters. So if the radius is 4 meters, that means that the length she's in contact with the half pipe in is this whole semicircle. And I know that the length then will be half a circumference. A total circumference is 2 pi r. Then semicircle circumference is going to be that length that we were talking about is going to be pi r. So that's going to be equal to pi multiplied by 4 meters. So then I know that the work done by non-conservative forces is going to be equal to minus half a joule multiplied by pi times 4 meters multiplied by the mass. So if I then go and plug in to the work energy theorem, I say the change in kinetic energy plus the change in potential energy is equal to the work done by non-conservative forces, which is exactly what I said up here in part C. It's precisely what I said. And I discovered that between 1 and 2, then that mgh is going to be equal to half mv1 squared plus the work done by non-conservative forces. So then I can sub in that equation, and I could say that mgh is equal to half mv1 squared plus this work plus minus half a joule multiplied by 4 pi meters multiplied by the mass. And you see then that if I divide both sides by m, the mass will go away. And then I'm left with gh is equal to half v1 is the 6 meters per second squared, half a joule, oops, that's a minus sign here, minus half joule multiplied by 4 pi. So if I sub in, then it's half times 36, that's 18, minus half times 4, that's 2 pi over g. So it's 18 meters squared per second squared minus half a joule, so that's 2 pi meter joule over g, which is 9.8 meter per second squared. And then you'll see that this is 18 minus 2 times pi. Pi is 3.14, so this is roughly 6 point something. 18 minus 6, that's 12 over 9.8 is roughly 1.2. And if you work it out, you'll find that it's 1.2 meters.